Hello, welcome to our SAE Automotive EMC Testing webinar. Thank you for joining us today. This webinar is being given by MET Laboratories. MET is a leader in the testing of electrical and electronic equipment for environmental hardiness, product safety, and electromagnetic compatibility. MET operates world-class labs in Baltimore, Maryland, Santa Clara and Union City, California, Austin, Texas, and also runs operations in China, Taiwan, Korea, and Italy. This webinar will run about 30 minutes with an additional 15 minutes for questions and answers. Due to the number of registrants, all attendees will have their phones muted. If you have a question, please type it in the questions area of your GoToWebinar control panel. We will attempt to answer all questions at the end. If you're having technical difficulties, you can contact us the same way or call us at 410-935-6053. That's 410-935-6053. We will try to resolve any problems quickly. Just a quick note on other upcoming events. Next month, MET is hosting a number of exciting things. On September 6th, we're hosting a webinar on Section 10 of GR 1089 for NEBS EMC testing. On September 13th, we'll have our annual Global Product Compliance Seminar and Crab Feast in Baltimore, featuring TCB Council Executive Director Chris Harvey and EPA Program Manager for Energy Star. And on September 20th and 27th, we have two wireless testing seminars, one on the East Coast and one on the West Coast, one in Baltimore, Maryland, and the other in Silicon Valley. You can register for any of these events at www.metlabs.com. Today's webinar is being presented by Asad Bajwa. Asad is Director of MET's EMC Lab. At this point, I will hand over the presentation to Asad.
Thank you, Barnaby. Hello, everyone. I'm Asad. Today we're going to talk about SAE Standards with the special emphasis on comparing them with the E-mark requirements and the big three, the three main automotive manufacturers, Ford, Chrysler, and General Motors. Here is a brief outline of my presentation. We'll start by exploring what are the North American automotive requirements. We'll have a comparison of E-mark versus SAE. SAE stands for Society of Automotive Engineers. Towards the end of the presentation, I will provide a little bit more details of how SAE comes into picture and under what mandate they've been authorized to write standards, and where does this standard stand in the overall picture of compliance for automotive products and the electronic sub-assemblies or electronic components for automotive. We will go over some of the main automotive standards which are commonly used. We'll do a comparison of the standards for full vehicle versus the standards for the components. Then we will briefly touch base with some of the compliance programs which are required by the big three manufacturers. These programs are under they are under A2LA flag, and this program goes by AEMCLRP, Automotive EMC Laboratory Recognition Program. And then we'll have a brief discussion about some of the most commonly done automotive standards and how do they differ from the testing done for the products which are used in commercial industry. Brief introduction of the EMC phenomena in our automotive environment. Why do we treat automotive EMC very different compared to the EMC in general for the products which would go into a central office, or the products which fall under quote-unquote IT category, or industrial or light industrial environment, so on and so forth. The primary reason there is that a vehicular environment by definition is very different from all the above. In the vehicle, first of all, there is no ground, there is no earth ground. Vehicle stands on, for example, a car stands on 4 wheels, which are insulating the metallic structure of the vehicle from the earth. So there are no direct means of grounding the vehicle to earth per se. So that introduces to a whole new set of challenges to how to get rid of the RF energy being produced by various electronic components which are installed or cramped into very small spaces on a vehicular environment. As we all know, more and more vehicles today heavily rely on the electronic subassemblies, looking from the ignition system to onboard computers to your steering, power steering, vehicle computer, automated the transmission system. Everything and anything and everything has or controlled by onboard computer, or have some means of electronic component there, which in turn would generate RF energy. And as all these components are being placed in very small space in a vehicular environment, so not only they become susceptible to the outside threats, by that I mean the threats which are the EMC threats which are coming from outside of the vehicle. Could it be a cell phone or a radio transmitter or a power grid or something? At the same time, they are a threat to each other. The components have to be designed in a way that they can withstand the EMI produced by each other. So radiation produced by one, the electric field produced by one, should not affect the functionality of any other electronic subassembly present within a vehicular environment. At the same time, vehicular environment is very different because it would have an onboard generator. It has a very high power batteries. There will be various different mechanisms which will create a high power switching, and those when those transients and when those switching phenomena happen, they lead to huge surges which can cause serious damage to the components if the electronic assemblies are not designed considering all those threats present. That said, at the same time, another threat would be electrostatic discharge. Like I said earlier, there are no means of grounding the vehicle, so people have to come up with a unique ways to deal with the ESD phenomena. And at the same time, the problem comes, which makes the ESD a very unique phenomena in a vehicular environment, is that the ESD model, which is used commonly referred as human body model, would be very different to the ESD model which will be used in a vehicular environment. Mm-hmm. There will be a few scenarios where one would have to consider before fully analyzing or dealing with the ESD problem on board a vehicle. One, a human being standing on the road and he touches a vehicle, or a human being inside the vehicle being charged due to the way his shoes are, what kind of the carpeting inside the vehicle, the way the vehicle is driving, so on and so forth. So all those things will add to the complexity of the problem. So continuing on, we will talk more towards as we go through the presentation about various standards and how they come into picture. My next slide is more on the same note as I mentioned earlier, that as the components are cramped so close, There could be so many different antennas due to the use of cell phones, Wi-Fi, other devices being used. So the threat level in a vehicular environment is way too higher from EMC perspective compared to any other product used in the industry. Now, what are the applicable standards? What are the requirements? Which regulations manufacturer or the electronic subassembly manufacturer would have to follow to be able to place their product in the market? So let's start to analyze that. Starting from North America, in USA, for example, FCC is responsible for the spectrum. FCC writes the rules for all the electronic products, for example, digital products, wireless products, cell phones, so on and so forth. Whether they are licensed or unlicensed, they all fall under FCC's regulation. However, FCC has certain exemptions as they are listed under section, I believe, 15. Due to those exemptions, some of the exemptions are for the products which will be used into controlled environment, like a fully controlled central office, and or controlled hospital facility. At the same time, the automotive products are exempt from the FCC requirements. When I say that, I want to be very clear. The exemption is only for the digital products. They are not required for FCC testing if they are designed for exclusive use in a vehicle. However, if there is a Wi-Fi device or any other sort of transmitter which could be used in a vehicle, they would obviously have to go through FCC approval process to get the certificate before they could use that product in a vehicle. So the exemption applies only for the digital products when they are designed exclusively for a vehicular environment. If we compare with the European Union has its own directives. The automotive products, vehicles, subassemblies, components for Europe all fall under automotive directives. However, the unique thing for the Europe is that depending upon which approach you may want to use, the product could fall under capital E or lowercase e. The primary difference between these two is that the manufacturer could get a lowercase e mark if they are applying the automotive directive. However, you can sell the product in Europe at the same time, equally likely, using the capital E mark. You can get the capital E mark if you are applying UN Regulation 10. The latest version of UN Regulation 10 is Rev 4. We'll have a brief look as we go through this presentation, and we'll talk more about the difference between E and capital E. In the following few slides, I have more description of what are the applicable standards, and we'll talk about that. I mentioned earlier, this slide lists basically the requirements for the Europe and the United States. We talked about the automotive directive, then we talked about ECE Regulation 4, I'm sorry, my apologies, ECE Regulation 10 with the Rev 4, and for United States, they are SAE Standards, and there are more standards by the manufacturers, and we'll explore that in a moment. Just a little bit more description on the E mark. A manufacturer of a component or vehicle can apply for E mark after successfully doing all the applicable testing which is required by either the automotive directive or by the Regulation 10. If you're going for Regulation 10, you get the capital E. The letter E indicates, signifies the approval for E mark. The number after the letter E indicates which nation the authorizing body, or if you want to call that notifying body, is physically located in. Then 10 is the regulation number. 03 indicates the revision. Latest revision is 04. Then afterwards, the 4 numbers indicate the approval number. Similar is the procedure for lowercase e. How do we compare the overall automotive standards present or being used worldwide? Oftentimes, a component manufacturer would want to sell their product not only to North America, but they would want to sell their product to worldwide. So for that reason, I have also listed the standards which are used internationally. If you look at the table, the first column is the list of the is basically a list of the standards. The second column basically shows the body who has been issuing these standards, the one who's been authorized to do that. The third column shows whether this standard or regulation or directive applies to full vehicle or whether it applies to electronic subassemblies. And then the last column obviously shows the release year or the date. So there are requirements, directives by the European Union. There are standards by ISO, and we'll talk about some of those ISO standards. One of the very commonly used ISO standards, both by which are referred by North American requirements, SAE requirements, and at the same time, the automotive requirements are ISO 7637-2, which talks about the transient immunity. Then there are requirements for ISO 11450-451 and 11452, which talk about some of the BCI and radiated susceptibility testing. Then there are, excuse me, then there are standards by IEC, CISPR 12, CISPR 25. CISPR 12 deals with the boards and stuff. CISPR 25 is primarily an emission standard which covers the narrowband and the broadband emission requirement for electronic components. SAE J551 and SAE J113 are two very commonly used SAE standards for approval process in North America. SAE J511 is for a whole vehicle, and SAE J113 is for the subassemblies. In the next few slides, we'll talk about that in a little bit more detail. ISO standards. Just want to spend a little bit extra time explaining how they come into picture. ISO 7637 has multiple parts, part 1, part 2, part 3, obviously. Part 2 basically deals with the transient immunity requirements on the power supply lines. Part 1 deals with 12-volt system, part 2 deals with 24-volt system. Similarly, the part 3 deals with both 12 and 24-volt system, which is basically being used using capacitive and inductive coupling mechanism. The 7637 is referred by Regulation 10. It's referred by Automotive Directive. It's also referred by majority of the immunity standards like J1455, J1113 series, so on and so forth. So this is a standard which is very, very commonly used and referred by other standards as a reference document. This slide shows some of the OEM EMC standards. At this point, I want to describe a little bit more how does the SAE EMC directive and the OEM standards correlate, compare with each other. With a special focus of this presentation on the North American requirement and SAE standards, even though for North America, for United States, there are standards under SAE mandate which manufacturer can use to have their product approved. However, the trick there is that the three big automotive manufacturers, Ford, GM, Chrysler, they will not buy a component or electronic subassembly from a vendor or a subassembly manufacturer unless the testing is done by our test lab, which is part of AEMCLRP program, which is Automotive EMC Laboratory Recognition Program. At the same time, these three big three we call are GM, Ford, and Chrysler. They have their own standards, which have a lot of similarities with their SAE counterparts. In many cases, they refer to those standards. However, these three big manufacturers, they have their own requirements. End of the day, they want the component manufacturer to do the testing for North America to their own requirements. Therefore, if you intend to sell your product to these big three manufacturers, you will have to go through a test program which will be done by a lab who is AEMCLRP approved. Here is a list of some of those worldwide OEM manufacturers who have their own standards: BMW, Chrysler, Ford and GM already I mentioned. Similarly, Nissan, Volkswagen, these folks have their own standards. So you would have to go through their requirement, which might be above and beyond the requirement by SAE, ISO, IEC, so on and so forth. Just a brief list of the Chrysler standard, Ford standards. I listed them just for reference only. This slide just talks about the GM requirements, the requirements for full vehicle, the requirements for the electronic subassembly. The three big manufacturers I mentioned earlier, they have their own test requirements. There are quite a few differences, but they do still have some commonalities. So this slide kind of summarizes what the common points are. For emission testing, the test method is primarily based on SAE J113 Then there is BSI test method, which is fairly similar. Then there is a conducted transient testing, which is fairly similar to ISO 7637-2. However, they may have slight deviation on the waveform, the amplitude, rise time, fall time, output impedances, but the generic test method is fairly simple. So this is just a basic summary of what the common test methods are between the three big manufacturers and the SAE requirements. As I mentioned earlier, I'll be talking about SAE a little bit more. SAE, as we know, stands for Society of Automotive Engineers. It's an international body. It has more than 84,000 members. They not only deal with the automobiles, they deal with the trucks, buses, aircraft, aerospace vehicles, so on and so forth. SAE was mandated by and was delegated by MC to write the standard for automotive products and the other products I mentioned above. So FCC, to just kind of recap, FCC rules do not apply to the digital products which are exclusively designed for or to be used on a vehicular environment. All those components, subassemblies are covered under SAE requirements. Now, a little bit more detailed discussion about SAE J551, and in the following slide, we will talk about SAE J113. SAE J551 primarily covers full vehicle. There are two approaches in the industry for automotive compliance, automotive approvals. First approach is to have all the components installed in a vehicle and have the entire vehicle go through the approval process. And if at the end of the day everything passes with the flying colors, product is compliant, full vehicle is compliant, it is considered that all the sub-assemblies in the vehicle are compliant. In the contrast, the other approach which is used more commonly is that we test all the electronic subassemblies or components separately, and each component gets its own approval, meaning it can be sold and it could be used, and then finally they are mounted on a full vehicle. So people use both approaches. Both have their pros and cons, depending on who the manufacturer is, who the suppliers are, how practical that is to have all the electronic components at a given time to go through the approval process. So all those factors help determine which approach a manufacturer would want to go. SAE J551, like I said, is for full vehicle approval. It has several parts, go all the way from 1 to 17. They talk about radiated emission, conducted emission. Conducted emission go all the way up to 18 gigahertz. Then there are narrowband, broadband emissions. Then they talk about many of the susceptibility testing, ESD testing, so on and so forth. Similar to J551, J1113 has several parts. Parts range from all the way from part 1, which is basic definitions and procedures, to part 42. I listed only few of them which are commonly used in the industry, but like I said, this series of standards is used for electronic subassembly or component testing. For example, ESD is covered by J11-13. Radiated susceptibility is covered by J11-22, so on and so forth. We talked about J551. We talked about J1113. It will be unfair to miss J1455 at this point. J1455 is a standard which is primarily written for surface vehicle. The title is Recommended Practice for Surface Vehicles. It, in essence, covers heavy-duty trucks. However, this is a standard which is very, very frequently requested by various automotive component manufacturers to show compliance, to show at least the minimum proof of the concept. The component or product being designed meets the minimum requirements for to be used in a vehicular environment. SAE J1455 has two main sections. The first section deals with the environmental requirements, which are like temperature, humidity, so on and so forth. The second part of the standard covers the EMC testing, which basically would cover radiated emission, radiated susceptibility, electrostatic discharge. Then it talks about various kind of transients, which are similar to pulse 1, 2, 3, 4, and 5 from ISO 7637-2. However, the waveforms are quite different. In addition, it has tests like mutual coupling, inductive switching, load dump, so on and so forth. Just for comparison purposes, I had a list of SAE standards from a J11 series showing the comparison with the ISO counterparts. For example, SAE J1113-41 deals with the emission testing, and the equivalent standard from the equivalent international standard would be CISPR-25. Similarly, J1113-11 deals with the power lead transient susceptibility, and the ISO equivalent is 7637-2. So it's a quick cheat sheet to show how the SAE standards would correlate with the international counterparts. Just another cheat sheet to show for what are the basic recommended tests for European markets. Obviously, if you are going for E-mark or capital E-mark, you will have to go through the full suite of the testing. But if you want to just show the proof of the concept that the product meets the minimum requirements, then commonly recommended tests are the emission under CISPR-25, basic immunity under 7637-2, and then some of the ESD testing to show the component can withstand the ESD stresses. Similarly, here is the recommended practice for North America. Emissions under J113-14, then immunity under 11 and 12, and finally the ESD testing, which is commonly requested, is covered by J1113-13. At this stage, I want to kind of briefly talk about a couple of very commonly used or commonly requested tests in the industry for automotive testing, and want to draw a brief comparison of them, how they differ from the commercial testing. The setup picture you guys are seeing on the screen is the radiated emission testing according to CISPR 25, according to J1113-41. Very similar setup. They both require a table which is like at least 25, which is at least 2.5 meter long. From the edge of the table need to have a metallic tabletop. Common practice is to use either aluminum or the copper. From the edge of the table towards the antenna side, we place all the components, lay the cables parallel to the edge of the table, separated by 10 centimeter. Then the table has to be at least 95 centimeter high. There is a separation between the edge of the table and the EUT boundary and the antenna of 1 meter. We bring various antennas to cover the entire frequency band. For low frequency, we use bicon, log periodic, so on and so forth, and horn antennas for high frequencies to cover the entire frequency band. So the primary difference from this setup compared to the commercial setup, in a commercial setup, you will be following a document like NCC 63.4, or you'll be following CISPR 16, where the testing is recommended to be done in a way that you set up your product on a non-metallic table. Could be wood, could be acrylic. With the high frequency testing, people would highly recommend using acrylic. It's recommended to have the table set up on a rotating turntable, which could go from 0 to 360 degrees. With the automotive testing, antenna is a fixed height antenna. However, in the commercial testing, antenna has to go from 1 meter to 4 meter, while turntable rotates from 0 to 360 degrees, back and forth, back and forth. So that is the main difference. Automotive testing, you are facing only one side of the EUT towards the antenna, which is considered the most sensitive side. However, in the commercial testing, you are looking at the entire picture. You're rotating the turntable to expose the entire 360 degree of the product to capture the highest emission coming out of the product. This is just a kind of I took a picture to show how our radiated emission testing setup looks for CISPR 25. Basically the same thing which we saw in the previous slide, just showing a physical setup, the antenna arrangements, so on and so forth. This setup picture shows a vehicular testing on the full vehicle, where a vehicle has been installed with all the components, electronic subassemblies, and then the testing is done on the finished product, which will be a vehicle in this case. The second test I want to talk about is the ESD testing. ESD testing, as we had a very brief discussion at the very beginning of the this presentation, creates a unique problem, primarily because there is no grounding. There are two main cases: handling and in-vehicle. So two different set of testing is required, and to simulate the problem happening into a vehicular environment, different ESD models are used. For handling, the discharging cap is 150 picofarad instead of 330 picofarad for commercial testing. For in-vehicle testing, the test methodology and test levels are defined by J11-13. The problem in the vehicular environment happens is that the charge can build up to more than 25 kilovolt, which can cause serious problems, serious threats to the various electronic components inside the vehicle. So care need to be taken to ensure all the electronic subassemblies have enough protection that they can withstand the charges up to 25 kilovolts or higher. At MET Labs, we have the ESD guns, which can easily go up to 30 kilovolt, and we have the ability to perform the ESD testing to all automotive manufacturers. Conducted transients. It is divided into two categories: transient emissions, transient susceptibility. Transient emission is a fairly simple test. There would be deviation from one standard to the other, meaning ISO 7637 compared to its SAE counterpart has a slightly different deviation as far as how the transient needs to be captured, the networks, so on and so forth. Transient susceptibility is covered by 7637-1 through all the way up to 3, depending on the power supply voltage, whether it's 12 volt or 24 volt. There are multiple pulses which are applied to the vehicle, depending upon the threat level, depending upon which part of the vehicle the component may be used. A different test level will be selected. The last test I want to talk about is the load dump test. Load dump test is potentially a very destructive test. The primary reason why it's so destructive is the nature or the root cause which generates this spike. Everybody knows, I believe, the Faraday's law that the rate of change of flux linkage, di over dt, leads to EMF or voltage. So imagine the car's generator is running. It's generating energy, and it's supplying a huge amount of current to the battery, or assuming battery is drained. Assuming a worst case scenario, hypothetically speaking, what if the battery cable breaks or gets damaged or disconnected somehow or the other? There will be no means to dissipate that energy, and due to sudden rate of change, say for example, we are pumping a current of 100 amps into the battery during the charging phase, and in practically zero time, in microseconds, for example, the current goes from 100 amps to 0. That is going to generate a huge di over dt, mere the fact of 100 by practically microseconds of the time, if not less. The voltage generated will be huge. That voltage, that amount of energy can be very, very catastrophic if the components are not carefully designed and not enough protection is built into the subassembly. So the load dump test is very, very commonly requested by the folks who are going for the SAE testing, whether it's J1455, whether it's J113 series, or whether it's the full vehicle under J551. Here's the picture of the transient for both load dump and for 12 volt and 24 volt system. At this point, I will conclude my presentation. Just a brief summary. We talked about why the automotive testing is different. We talked about how and where the SAE testing comes into picture. We talked about the comparison of SAE requirements to their international counterparts, IEC, ISO, the European requirements under EMARC, the UN regulations, and we talked very briefly about the requirements by the 3 big manufacturers in North America, GM, Ford, Chrysler. We also talked about the AEMCLRP program, which is a must for if we want to test for the 3 big manufacturers. With that, I conclude my presentation. If you folks have any questions, I will be very glad to help answer. Thank you very much. Barnaby, back to you.
Great. Thank you, Asad. As Asad said, that concludes the presentation portion of this webinar. A copy of this webinar will be available on metlabs.com. We will send a follow-up email with a link to this file. Now is the time when we will answer questions. If you have a question, please type it in the questions area of your control panel. For questions we can easily address now, we will read the question aloud, then give the answer. Give us just a minute to get oriented with these questions.
There is a question about what's the main difference between EMARC versus lowercase EMARC versus the uppercase EMARC. As I mentioned during the presentation, that manufacturer can get the lowercase EMARC if they are following the automotive directive, whereas the manufacturer can get the uppercase EMARC if they are applying for the approval under the UN Regulation 10. There is one more question about which MET Labs locations are approved for EMARC testing. We do EMARC testing from primarily from our Santa Clara location. We have partners around the world who help us support go through the EMARC approval. So the testing is done in Santa Clara, and using that test results, we work with our partners to help issue the EMARC approvals.